The 5 is more difficult than complicated than S3.
And bigger or equal than 5. All of these groups are simple. This is going to be anyone else? Nikita, what's your favorite simple group?
Baby monster.
What is a simple group?
What is that?
Baby monster.
Huh?
What is a
Baby
simple
monster. Baby monster is good. Baby monster is good. I don't know what it is, but it's good. Actually, you can, while I'm talking, you can Google Atlas of finite group and representation, and actually all of them are classified. You actually choose the one you like. Baby monster.
PSL.
Yes. PSL. Which PSL? Almost all PSL. PSL NQ, and this means field of Q elements. P to the R, which is Q. And I think for almost all N and Q is simple, with few exceptions. Okay, maybe for N equal like 2, Q equal 2 or something. With few exceptions, this is simple. It's a series, yeah? Okay, how to merge these two guys? We need to have some common objects, and actually we'll do something. So we can ask a question. So we have this bunch of these groups. Okay, one, yeah. Are they means this group, contained in the group of birational automorphism of P2, which is usually called Cremona group. Okay, so I assume the surface is rational, so it means it's birationally equivalent to P2. There's some transformation. So group of birational automorphism of this surface is the same as this surface. Yeah. And this group is actually well known, it's classical, is generated by PJ3C and one involution, which is known as Cremona involution. Tau sends point x, y, z to point 1 over x, 1 over y, 1 over z. But this is actually a big group. This is a large group. Because this group, and when we want to answer this question, we should keep in mind that G acts on P2 rationally, not regularly. So we cannot just study it using usual tools. But what we can do, we can always resolve these points of indeterminacy of action of this group here. So if you assume our group is a subgroup here, we always can resolve, blow up, and get some surface S, such that this group G is actually contained in the group of automorphism of S.
So you do resolve non-singularities.
Okay, let me even put it this way. I don't like this. Let me put it. I can birationally transform P2 such that we have this. Yeah, S is some surface. This construction actually is pure algebraic. Because what is this group? This group is actually a group of algebra automorphism of basically this field. Yeah, and to get this S, first things you do, you take the fixed subfield, and you take some its model. This is a algebra. This is a field which has finite transcendence degree. You can take some of its model I, and then you can take its normalization back in this field. And once you get this, this is your S.
What's Y again?
Y you can you take this as a field,
Yeah.
but for every field of finite transcendence degree over complex numbers, it's a field of rational functions of some algebraic variety. And I just take some model, some projective model. It's not unique, but it exists. And then I take the normalization of this guy in this field, and it's unique. And then the group G, it's actually birational to P2, in this case, and group G acts biregular here. This construction, this map is pure algebra. There's no geometry here. But in this way, the surface S can be arbitrarily bad, but it's normal. And then we can apply the same thing here, but now everything becomes G invariant. Everything becomes G invariant. So basically what I want to say, let me just show how this picture and some other stuff can actually answer this question immediately in the easy way actually I can answer it explicitly, but the easy point is actually I can answer them for sufficiently large group. So if I just say, okay, here infinitely many groups, here infinitely many groups, It is one group, but it's monster, baby monster, but still. So for all of them sufficiently big, I can use this scheme, these ideas, to answer this question very explicitly. Basically, answer should be no. We know, yeah, it's a lot of groups, but this is one group, so why should they all live here? But on the other hand, this group is big. So for example, this question, it may look naive, and we intuitively, answer should be no for most of the groups, but it's not so naive. For example, 15 years ago, Ser, when visited actually Edinburgh, on a workshop about Cremona group, Ser asked a question, is it true that there exists finite subgroup which is not contained in the group of birational automorphism of the full space? If I put here 3, okay, Ser of course knew everything about this group and he had some results about this group. So Ser asked a question, if I put here 3, not 2, Ser asked a question, does this group contains all finite groups or not? So it's not so naive as it is. And okay, and we also answer this question as well. So okay, let me add this picture. So we have some group G acting here biregularly, yeah, and then we can have G equivariant minimal resolution. Actually, it's the same because I don't even need to put G because it's minimal, it's unique, it's automatically G equivalent. So this arrow automatically G equivalent. Okay, unfortunately, this arrow is not. So this arrow is not unique. This is unique, but this is not. So here, you must choose it equivalently. So it's an extra condition. We choose G, this contraction of -1 curve, in G equivalent way. G equivalent way. And unfortunately, the picture doesn't change. We don't have this simple picture anymore. I cannot conclude that this is P2 because it's I contract -1 curve which lies in the orbit of this group G and they disjoint. They must be disjoint. So it's actually a complicated process. So I still get this guy, some minimal, but then the only thing I know, I have two options. Either equivariant Picard group is Z, and then it's clearly I cannot contract anything if equivariant Picard group is Z. Each time I contract something, my equivariant Picard group actually drops by 1 at each step. So if I have this picture, I cannot contract anything. Or, again, I have to erase Fn for the moment, or I have some surface with equivariant Picard group Z2, and then I have a map to P1 such that general fiber is P1. Some fiber maybe not P1, but general fiber gonna be P1. And this is usually called conic bundle. Yeah, and this is equivariant. This is G equivariant map. G. So I have very similar picture, but the final model is not so simple as P2 or Fn. It may be, yeah, but let me look closely.
But it's obvious that you have such a minimal model.
Not obvious. The question is like, you can rephrase this question for trivial. Is it obvious that you can actually contract -1 curve?
It's known to
It's not obvious, but it's known to exist. So the same is here.
Yeah.
Its proof is essentially the same. So, but you have to add, you take a proof from every book about this, and you just add a G equivalent. And then the proof works absolutely the same. So in many, because of this, the proof of this usually is not even written clearly because it's the same proof as a standard contraction of -1 curve. Okay, so let's look closely at this guy. So suppose we have this nice special case. Let me use a black one. Yeah, what can we say? What can we say about this? So suppose we have this S minimal with this condition that equivariant Picard group G of S is actually Z. So if Z is generated by some guy, some divisor, but since I assume everything is projective, this divisor should be ample by definition, because my surface must have at least one ample. It means like a basically hyperplane section. So this is what's called, okay, what is ample? Let me mention. So if you don't, what is ample? Ample basically, okay, formal definition, you take multiple of this